It's a great pleasure to introduce Professor Joseph Samuel, Sam, to all of us here for this Vignyana Kathegalu. I know that everybody knows Sam here, but I will still do a little detour and say a few words about his past. Nothing sinister, I assure you. Sam finished his MSc, integrated MSc from IIT Kanpur, and then did his PhD at IISc with Professor Mukunda. And I think even before he finished, he started off at RRI in 1982, and he's been in RRI ever since until he then moved after retirement, after his emeritus position, he moved to ICTS, where he is right now. One of his most cited works, over 1,000 citations, is this work that he did along with Professor Bhandari on the Berry phase. It's one of those works that gets cited even today, 2022, there's still people citing him. And this was a work where he basically generalized the idea of Berry phase to more general contexts. That it wasn't just in the particular context that other people had studied it, that it was much wider a phenomena. And ever since then, he's been engaged with questions on the Berry phase. But I want to point to something. As a quantum person in quantum gravity, I first knew Sam as a person who had actually contributed very important work to quantum gravity, in particular on Ashtekar variables. And while he was at RRI, he then spent a few years in the US as a visiting professor, first in Utah, and then at Syracuse, where Ashtekar was. And he had already contributed very significant work to the Ashtekar, this new approach to quantum gravity, using these so-called Ashtekar-Sen variables. That work, again, has been very, very important, has been cited extensively, and was very much a part of the contributing literature to Ashtekar variables. And he continued this. He didn't stop doing other things, but he was, I would call, a quantum gravitist until around 2000, where he wrote a somewhat iconoclastic paper on the same. And I think that was, again, a very important paper. But of course, all along the way, he continued to have an interest in and work in a variety of different kinds of physics. And also with a wide range of people, from mathematicians on one end, to other theoretical physicists, to experimentalists, like many of you know here, and from polymer physics to atom interferometry to quantum information, and now most recently onto Kähler structures, which is like hardcore mathematics. So the range of things that Sam has worked on is quite incredible. I mean, just looking at at his publication list is quite a revelation. And I personally shared a very happy collaboration with him a few years ago in general relativity. And he's also written a lot of popular science articles and given a lot of popular science talks. So that's also very much a part of who Sam is as a physicist. He shares his physics with people, and that's what I hope he's going to do today. I also want to end by saying a few maybe embarrassing things about Sam, but bear with me. I think in many ways I consider him to be the epitome of a scholar. He's not driven by fashion, but nevertheless he's able to adapt to different kinds of physics. I mean, he has such a wide range of interests, and he's not constrained by training. He learns new things quickly, and he works on different areas and contributes significantly. And I think I can call him a polymath, but without the swagger. Okay, so Sam, despite all of this great stuff, is a wonderful person to know. He's a really accomplished guitarist and a lot of fun to hang out with. So without further ado, here's Sam.
Thank you, Sumati. That was very kind of you. I hope I can live up to that introduction, but I will give it a try. One of the things in my favor is that the title of the series is Vignyana Kathegalu, and that means stories about science. And I want to thank Tarun for inviting me to talk in this forum. And one of the things I like about stories is that they don't have to be true. So I'm going to entertain you with some stories, not all of which will be true. In fact, they are true in a very, there is some element of grain of truth in it, but whether or not the stories are true, I flatter myself that they will be instructive. So the title of my talk is The Finite Part of Infinity. This is an equation that appears in one of Ramanujam's notebooks. It's not that he discovered it, but it's been done by others before. But this equation, he discovered it independently. So how many of you have seen this equation before? Please raise your hands. Okay, quite a large number. And how many have not seen this equation before? An equal number. And how many of you are too shy to raise your hands? Okay, so I'm going to address it to all those people who haven't seen this equation before or have been too shy to raise their hands. So this equation looks paradoxical on the face of it. If you look at the left-hand side, it seems wrong on so many levels. You're adding integers to get a fraction. That's never been done before. You're adding positive numbers to get a negative number. Neither has that been done before. So is this a scam? And the main point of my talk is contained in this answer. No, it's not a scam. It's an absolutely, brilliant equation. That's the best way to describe it. I won't say whether it's right or wrong. We'll come to that later. And it took somebody like Ramanujam's or somebody of his quality to discover it. There's a lot that we can learn from this equation, and that's really what I'm going to talk about in this talk. There's the deep mathematics of divergence series. It embodies some techniques which are useful in theoretical physics. It can make predictions about real experiments in the laboratory. And what I'm talking about is the Casimir effect, which is a very strange effect that was discovered by Casimir. You take two copper plates and put them a certain distance apart, and they will attract each other. There's no charge on either of the plates, and there's no repulsion because of, they're neutral plates. They're conducting plates, but neutral plates, and you'll find that they attract each other. It's a tiny force which has actually been measured in the laboratory, and this is a simple example of how we make sense of infinities that appear in physical theories. We all know that when we do quantum field theory, there are infinities that show up which have to be tamed. For example, in string theory, the dimension of b equal to 26 is favored because of this identity. The way in which it works is that in 26 dimensions, a string has got 24 transverse dimensions. And when you put this minus 12, 112 with the 2, which came in the, a 2 will show up later, you'll get 24. And one can understand the 26 dimensions of string theory just from this equation. Now, as I said before, I will not, I don't think I said this before, but I'm going to address this to the graduate student population of this institute. Some of you might find it elementary, and that's the right level to pitch it at, because it's actually, although it's a public lecture, I noticed that the audience in most of these talks is not from the general public, but people who have some background in mathematics. So this is the rough outline of my talk. The introduction, which you just heard, is about 5 minutes. The convergence and divergence series, mathematics part, will be another 20 minutes. The physics will be another 20 minutes, the Casimir effect. The conclusion will be 5 minutes, and afterwards I'll have a small outro about the surface tension and the cosmological constant, which is a topic I've been interested in. This is more on the research side. The pedagogical part is in the first part. I will be pausing for questions at these points, And the reason for doing so is that there are some people online who may not find a chance to ask these questions. Of course, you're welcome to interrupt me in between also. In your schools, you have all learned about these two progressions, the arithmetic progression, where the difference between successive terms is constant, and the geometric progression, where the ratio between subsequent terms is constant. So all of you know about the AP and the GP, the geometric progression and the arithmetic progression. One can also talk about the arithmetic series, which is the sum of the first of these terms in the progression. And similarly, the geometric series, 1 plus half plus 1/4 plus 1/5, etc. So these days, although we use the word progression in school, it's called a sequence. There's a set of numbers labeled by an integer, an, which goes off to infinity. When we talk about series, we can talk about the partial sum. Take the first n terms of the series and sum them together, of the sequence, and sum them together. And that is the partial sum, which I'll call Sn. For the arithmetic series, it's very easy to do. Sn turns out to be n into n plus 1 over 2, the one that I mentioned before. And there's a story behind this. This is the first of many stories which may or may not be true. So the story is that Gauss, when he was in school at the age of 7, was sitting in his class when the teacher assigned them a problem. The problem was to add up the first 100 numbers. Of course, all the kids were struggling with this. And the custom in the school was that you would write the answer down on a slate and turn it face down on the teacher's desk so that the others didn't see. Gauss immediately wrote the answer and put it down, and one by one the other slates followed. At the end of the day, when they looked at all the slates, there was only one correct answer, the first one that was due to Gauss. And probably the way he did it is that he had obviously thought about this before. He wrote down all the numbers. Suppose we were adding the numbers from 1 up to 10. So this is the sum you're interested in working out. And then he wrote it again backwards. Now when you add these two terms, you find that 2s is equal to the sum of all these guys, which is 11 this way into 10 this way. And that tells you that s is equal to 55. A very similar argument tells you that the answer is 5050 for the arithmetic progression up to 100. So this story has got, it's actually a very dubious story, because the original story, which I found out while I was preparing for this talk, is that at his funeral oration, one of his friends said that Gauss was very fond of telling this story, but it was a slightly different story. It was not this particular arithmetic progression, but it was something else. And there's no mention there of Gauss having used this method of finding it. Nevertheless, the story is instructive, because the idea behind such a thing, which is probably what Gauss used, is that you see patterns which are larger than the problem which you're trying to address. So that's the instructive part of the story. The truth is very dubious, of course, like all the stories I'm going to tell today. The geometric series, similarly, you can solve by a very similar method. You write down the series and then write down r times Sn, and then you solve for Sn, and you find this answer, which you have all learned in school. The finite series are perfectly well defined. What gets interesting is when you make the series infinite. Can we assign a value to the infinite series? And this is an example of a question that has plagued humanity for centuries. If you go back to the ancient Greeks, Zeno was able to prove that Achilles would never overtake the tortoise, because by the time he got to the tortoise, where the tortoise was, the tortoise would have moved, and so on it goes. So you have to sum an infinite series to get the answer, and they didn't know how to do that. So can we assign a value to infinite series is a question that did not bother Euler as much as it should have. He assumed it was possible, and he was used to manipulating with infinite series, and he was very good at it. It takes some special skill, and Euler certainly had the skill to only come up with correct equations while manipulating infinite series. Ramanujam also played with infinite series. I must say that these two were two very intuitive mathematicians who threw grammar to the winds and used their intuition to guide them without making too many mistakes. And in fact, with Ramanujan, even the mistakes he made were interesting mistakes. So that led to new branches of mathematics. Now, Cauchy was of the opposite persuasion. There is a very careful mathematician who's used to rigor, Gaussian rigor. So Cauchy's answer was yes, if the series converges. And he used the notion of a limit. If the sequence Sn of partial sums tends to a finite limit, then the series converges and you can give it a meaning. Now, the arithmetic series does not converge. It keeps on going forever. The terms get bigger and bigger, or, either go to plus infinity or to minus infinity. So how do we assign a value to this infinite series? For the geometric series, it's quite easy. It converges if R modulus is less than 1. So it's very easy to see. You take a square like this, you write 1 there, and you take another square, write half, and then you divide each time by half, and then you see that the sum of all these terms, which I've written in color code, adds up to 2, which is the area of the two squares. And the general formula is this one, which is only valid when mod R is less than or equal to 1. In this case, if the series converges, Cauchy, Ramanujan, and Euler will all agree on the value of the series. But now let's get more adventurous. Ramanujan was now pushing boundaries. Let R approach -1, which is the boundary of where the series will break down. So you write 1 over 1 minus -1, and that is half. And you will write that as 1 minus 1 plus 1 up to infinity. Now this is the dubious equation. It's called the Grandi series, and there were many people apart from Euler, many others who also played with infinite series. Grandi was one of them. And he assigned the value of half to this series. More formally, I can think of taming the infinity by taking this thing and putting in an extra converging factor, e to the minus lambda n. Now this is now a geometric series which will converge if lambda is positive, and let lambda tend to 0 from positive values. And then you'll find that this thing actually tends to half when you take the lambda to 0. It's a very simple calculation which I have done several times. There's also another sense in which this makes sense. If you look at the partial sums of this series, they alternate between 0 and 1. They go from 1 to 0 and 0 to 1, back and forth. And if you take the average of all these excursions, you get a half. That's called Cesaro summation. There's another person who tried to make sense of infinite series. There are many other people who have different rules, and all of them agree when they do, but some rules work when others don't. For example, Grandi series, this method of Cesaro summation does not work for our series, the one that I started the lecture with. Yeah.
Add a -1 to that, overall it's -half.
Yeah, that's right. So that's an example of a manipulation which is not allowed in this game. Yeah. So let's take this series S, which is the geometric series, and it's valid for R all over the complex plane. Sorry, within the unit circle, it's valid. And if I multiply it by itself, term by term, and this is the kind of thing that Euler was very fond of doing, you'll find that 1 over 1 minus R whole squared is 1 plus 2R, because you get 1R from here multiplying these two, another one from multiplying these two, plus 3R squared, plus 4R cubed, etc. Now if you let R tend to -1, the left-hand side goes to 1 upon 4, the square of the Grandi series, and the right-hand side goes to a series which has got almost the same form as Ramanujan's sum, except that there are some minus signs. Let's press on then. The Ramanujan sum is this one. I'll add it to 4 times itself and align the terms like this. And then when you add these, you'll find that when you subtract the second equation from the first, you'll find that -3 times the Ramanujan sum is the same as this sum, which we had earlier worked out to be 1/4. You can solve this equation to conclude that 1 plus 2 plus 3 up to infinity is equal to -1/12, which is how Ramanujan did this series. Alternatively, we can use the idea of forcing convergence by putting in some exponential damping of some kind to make the term smaller. And then you find that this sum is replaced by this one, which is also a doable sum. You can write it as d by d lambda of a geometric series, and afterwards find the value of this function, which is the function of alpha, which actually diverges when lambda tends to 0. Now that is this term here, minus 1 upon lambda squared. But then you get a minus 1/12 as a finite part, and you get some other stuff that goes to 0 when lambda goes to 0. So what that means now is that this is the infinite part of the series, and this is the finite part, and that's the title of my talk, the finite part of infinity. The whole thing on the left-hand side is really infinite, but it has an infinite part and a certain well-defined finite part. We're going to understand in what sense that is well-defined and unique. So I should add a cautionary note here. Manipulating divergence series without a valid license can be injurious to your mental health. And Sumati just brought up an example of that. You can get -1, well, you can get -half if you like, for the same series. And you'll end up as a train wreck. I did not see this coming. You started out with a logical set of axioms or mathematical ideas, and you ended up with a contradiction, which is the worst thing that can happen to you in mathematics. For example, I can get 0 if I group the terms like this, and I can get 1 if I group the terms like this. I conclude that 1 is equal to 0, and that's a contradiction. Now, a contradiction is a disaster in mathematics. It's the mathematical equivalent of a train wreck. But in poetry, it's perfectly all right. There's a poet called Walt Whitman who writes, "Do I contradict myself? Very well then, I contradict myself. I'm large, I contain multitudes." So mathematicians cannot contain the same multitudes that poets can. So we have to do something about such contradictions and come up with sets of rules that will only lead to consistencies. In fact, Bertrand Russell, a great philosopher, was fond of saying, given a contradiction, one can prove anything. This is another one of the stories which I'm going to tell you, whose truth is dubious, but whose instruction is indisputable. So he was so fond of saying this that he used to say it over and over again until his friends got sick of him. And one of his friends who got sick of him said, "All right, Bertrand, I'll give you that 1 is equal to 0. Can you prove to me that you're the Pope?" I mean, this is a loaded message. Actually, Bertrand was a staunch atheist, and the Pope is, of course, a staunch theist. So here's Russell's answer to this challenge. Right, start with 1 equal to 0, add 1 to both sides, get that 2 is equal to 1. I am 1 and the Pope is 1. Together we are 2. But 2 equals 1, so the Pope and I are 1. QED. So to avoid contradictions, we need a consistent theory of divergence series based on general axioms, and one such is given by complex analysis and analytic continuation. As we work on the complex plane, actually even Euler was familiar with the complex plane. He also worked there, but it was not explored in his day as roundly as it was later by people like Bernard Riemann. And Riemann introduced the Zeta function. This is a function which is an infinite series of the complex plane. It's 1 upon n to the power of s. There's a very deep bit of mathematics here. This has got information about prime numbers. Surprisingly, it connects analytic the theory on the complex plane to the prime numbers and number theory. So this function is well defined. The series converges when the real part of s is greater than 1. And the function diverges for s equal to 1 when it becomes the harmonic series, 1 plus half plus 1/3, etc. We can extend this function to the rest of the complex plane by analytical continuation, and this is one method of getting finite answers from divergence series. That is, you go to the complex plane and do an analytic continuation.
Actually, my at the very beginning, when you write the function -1 to the power n,
Yes.
you can write also e to the power I pi n, and then
Yes,
you write
yes.
the I pi cos of I pi.
That's true.
I into sin pi.
Yes.
Any arbitrary way, then you can represent this circle.
Yeah.
Circle more pictorial.
That's absolutely right.
Point.
Yes. Any other comments or questions? Yeah.
Is 1 minus 1
Yeah.
plus 1 minus 1, how it is 0?
Yeah, no, because when I group the terms,
That is 0 into infinity, right?
let's see, where was it? Downstairs here. Yeah.
Yeah.
So you're saying there's an infinite number of.
0 plus 0.
Yeah.
So that is 0 into infinity.
But if you keep adding zeros,
Yeah, but infinite times, right?
okay, it's a doubtful
How
thing.
do
Yeah.
you know that it is?
You're saying that you could live with this equation.
Yeah.
Yeah. Okay. Okay.
That's not defined.
Yeah.
How you can see? No? How this sum you can see?
You're going to get us all to be train wrecks.
Yeah. No, because you can also get. Yeah. You-
0 into infinity.
But will you get 1 from that? 0 into infinity, you might get 2. And then 2 will be equal to 1.
Not defined.
Okay, it's ill-defined. Yeah. So then you have to say that all the infinite series are ill-defined. Yeah. But that's not the approach.
Not all, but
The approach we're taking is to see if we can make sense, give a meaning, a consistent theory for infinite series. Yeah. But you're right. That's also an example of the train wreck business, no? Of ending up with a contradiction. And we've seen that contradiction makes the whole edifice fall apart. That you build up a theory of mathematics, and then if you find even one contradiction, you can prove anything. For example, you can prove a theorem, and you can prove the negation of that theorem. So you don't have mathematics anymore. It's a logical structure, and we're trying to build it up, and what we want to avoid is a contradiction.
Total number remains the same in both the equations.
Total, no, it's all infinite. We don't know what the infinity is. Each, yeah. Yes, please.
The cancellation of infinities, I mean, when we did the calculation again, and we got 1 over lambda squared minus 1 over 2. In Ramanujan's way of doing the cancellation, was the cancellation of that first infinity because he sort of subtracted 2 infinite series when he took SR minus 4 SR.
We will come to that in this part of the talk. It's exactly that. So now I'll switch to physics. That was all pure mathematics. So the physics of the Casimir effect involves some quantum physics and very simple quantum physics of the harmonic oscillator. We all know that if you take a harmonic oscillator, which you've all studied in your masters, classically the lowest energy is at rest at the bottom of the harmonic potential. It has got 0 energy. So if you go to a playground, all the swings, when they come to rest at the end of the day when the children have gone home, they settle down into the lowest energy state, which is at the bottom of the well. But this is not allowed quantum mechanically. It's forbidden by the uncertainty principle. And there's a kind of motion, which is 0-point motion, that gives it a finite amount of potential and kinetic energy. And the 0-point energy has got the value h bar omega by 2. So this was the 2 that made 12 of the Ramanujan series into 24 of the number of transverse dimensions of the string. So we have to count this energy now, and I think that you will all believe that the dimensions are right. H bar omega by 2 does have the dimensions of energy, because h bar has got the dimensions of action, and this has got the dimensions of inverse time. No, I'm going to get there later. Yeah. I'm just starting with saying the quantum physics that we're using is just this term, h bar omega by 2. An oscillator has got this much energy, whether you like it or not, when you leave it alone. Now let's look at a bow string, and I've made a simple, here is a bow. And when you want to shoot an arrow, you have to pull the bow back. I made a small bow here, which is not as fancy as that one over there. But you will agree that if I pull this bow back to shoot an arrow, the ends will come together. You can see the ends stretching, right? If I distort the string, these two ends are brought together. There's a force pulling the ends together. Now, suppose I let it go and the string is oscillating. It's still deviating from a straight line. So the ends will still be brought together. So your physical intuition tells you that there's an attractive force between the ends. Let's try to calculate this attractive force. a string has got an infinite number of modes. Every mode is an oscillator. You can have the fundamental, the second harmonic, the third harmonic, the fourth harmonic, all the way up to infinity. So that is, the string can be thought of as a collection of oscillators. And I told you that we're talking about quantum fluctuations, but it's also well to remember that there are also thermal fluctuations. At a finite temperature, there would be thermal fluctuations of the string, which also would have the effect of bringing the ends together. But let's focus on the quantum fluctuations now. So the Casimir effect is the following effect. Take the fundamental frequency, which is given by the speed of sound in the string, and pi over L, where L is the length of the string. The speed of sound is square root of the tension divided by the mass density per unit length.
Ends are then they pull together, but they also come back, right? So they're oscillating.
Yes,
As
yeah.
you pull it, of course, as it goes.
Yeah,
fast.
that's very good, yeah. So when you pull the string, it comes together and moves back and moves to the other side. It also comes together. So the net effect is whether you pull it this way or that way, it's always pulling together. So the time average is always bringing it together. Then you get a sine squared, which averages to half. Yes.
Oscillating within that.
Yes. But the net effect is an attractive force because it oscillated. You have a sine squared averages to half.
And the distance between the edge slowly decreases as the
Yes, yes. As you keep pulling it, it'll keep decreasing until it breaks, which is what happened to Rama at some point. Right?
that is in the average time.
So now, if I take the equation which I had earlier and work out the energy in the 0-point motion, that is E of L, it depends on the length, and it is h bar c. I mean, I think that the frequency was given by h bar, well, frequency is given by speed of sound times pi over L, which is up here, the fundamental frequency, h bar over L, and then there is an n here for the mode, and I have to sum this series all the way up to infinity. So this much energy is sitting in the 0-point motion. And shouldn't there be a factor of 2 here? No, because actually the string oscillates in both directions. Both, if the string is like this, it oscillates like this as well as like that. So energy is a function of length, has the effect, looks like this. It looks like 1 upon length. As the length increases, the energy decreases. This will tell you that actually the force which we calculated is going to be repulsive. It's going to push it apart.
Two infinite planes, right?
No, I'm talking about just a string on a bow. This guy. This one is a finite thing. Yeah. Yeah. This seems to diverge because of the sum over n, and it seems to have the wrong sign. There's infinite number of oscillators, one for each n. And I told you that there's an infinite number of modes in a string, but that's another thing which is not true. There's actually a finite number of modes because there are wavelengths which are so small that they are smaller than the interatomic spacing. So it's not really an infinite sum, but it's a finite sum. It goes up to a finite value, and then after that the modes don't contribute at all. This is the physical way of understanding it. Yes, please.
So you are only considering transverse mode of.
Yes, yeah. There are also longitudinal modes which have a higher frequency. Yeah, that's also true.
But if we can safely ignore it, is it?
It will give a similar answer. If you include it, it will give a similar answer with a more complicated calculation. Yeah, for photons, it turns out there are only transverse modes. That's why I'm sticking to the transverse modes. Yes.
Yeah, so even larger wavelengths are also not supported, right? Because
That's true.
very-
Yeah, yeah. So we start from 1. We start from 1 to infinity, where 1 is the fundamental frequency. Yeah. Yeah, maybe if you use the mic, the questions will get recorded, or, yeah.
So coming back to, so I'm still confused about only transverse mode. For photon, I can understand what you are
Yes,
saying.
right.
But suppose it's a string with so then wouldn't that add to?
It will also add, but it'll be exactly the same problem with a slightly different coefficient. There'll be a different omega, but the sum over n will still be the same thing, because there also you have n sum over modes. So you'll have h bar omega 1 by 2, let's say, times sum over n, plus a different omega, for the longitudinal modes, because the longitudinal modes are of higher frequency. So now let's apply the idea that you don't really sum over an infinite number of modes. The sum needs a regulator, and that's what we had earlier, even in the mathematical treatment. I put in the sum, but I put in this regulator, which is something which dies out for large n. As n gets very large, this term goes to 0, and the series is finite, effectively finite. I do this calculation, and I find that the energy is given by an infinite part, which is sitting here, plus a finite part, which is sitting here, plus another part that goes to 0 as lambda goes to 0. Yeah? So I seem to have extracted the minus 1/12 from this, from the physics end as well.
Just and see the 0 point of oscillation.
Yeah, the 0 point calculation is giving me this minus 1/12. Now,
But in the Harmonic series that you have shown in the beginning is minus 1/12 come as a constant only.
yeah. So we only measure forces in the experiment. When we go to a lab, we're not really measuring energies. We're only measuring forces, and forces correspond to differences of energy. So what happens when L goes to infinity? Suppose I define x equal to n over L and treat x as a continuous variable when L goes to infinity. Then dx is equal to 1 upon L, and as L goes to infinity, the same sum we wrote down becomes something that looks like this. And this term exactly equals the divergent term in the sum. So for an infinite string also there is an identical term, and what we are concerned about is differentiating with respect to L. So we leave out this constant when we are talking about forces. So the term that we had for the energy has this divergent term, and when L goes to infinity, that same divergent term is here, and if you look at derivatives, that's going to drop out. This is the interesting thing here. And the finite difference and of negative sign, you find that there's an attractive force finally. This zeta of minus 1 is the zeta function which I had earlier. Its value is minus 1/12, and so this is an attractive force. So we recover the physical intuition after going through all this mathematical gymnastics. Yeah, we expected an attractive force, and we finally got it by realizing that energy is not being measured in the Casimir experiment, only the force is being measured. Now we'll switch from a mechanical system to an electromagnetic system, and the argument is virtually identical, except that we escape the pitfall that Saptarishi pointed out. There are no longitudinal modes for photons, there are only transverse modes. I take a metal guide of waveguide of length L, put some 2 copper plates at the ends. The speed of sound is replaced by the speed of light, and very high frequencies pass through the tube, and so they are not counted. Because of the atomistic nature of matter, we really do not have an infinite sum as I've written here, but we can use the infinite sum to guess what is the force between the 2 copper plates at the ends. And this is the Casimir effect, except that I've done this in 1 dimension. I deliberately started from a mechanical example because that's more familiar to our intuition, and now I've gone over to the electromagnetic example, which may not be that familiar. When we go to 3 dimensions, this is the actual Casimir experiment. You take 2 parallel plates of area A and separation L. You do a very similar calculation, except that it's now n cubed, which you have to sum from 1 to infinity. When you do that, you find that this is the Riemann zeta function evaluated at minus 3, and its value is 120. And you find again that there's an attractive force that takes, after you remove the infinities, by taking away the energy of an infinite separation, that the force between the 2 plates which is attractive. And that is the Casimir effect. And we have understood the Casimir effect by a complicated mathematical idea and also from a simple physical idea, that you have a cutoff. The exact form of the regulator is not important. One can show that. You can show by using the Euler-Mclaren series, which tells you the difference between the sum and the integral, and some integration by parts, a trick that Euler loved. And you end up with understanding Bernoulli numbers as well and relating them to the Riemann Zeta function. So the experiment is that, well, Casimir proposed the theory for electromagnetic systems, and then this experiment was done, but the uncertainties in this experiment were as large as the predicted theory, so it was not that conclusive. Then Lamoureux did an experiment with a plate and a sphere, and that was true to 5% accuracy. The difficulty with having two parallel plates in an experiment is that it's very hard to keep them parallel. If they're even slightly off parallel, you get all kinds of crazy answers. So the experiment that was done by Lamoureux involved a plate and a sphere, and you can approximate a plate by a large sphere. It's easier to just keep a plate and a sphere and measure the separation between them by using optical tweezers. And a better version of this experiment was done by Mohiddin and Roy. This is Roy, who's now in IIT Kharagpur. In 1997, they got the accuracy down to 1% using an atomic force microscope. And there are further refinements. I don't need to go into all of them, but there's no doubt that the experiment agrees with the theory. So any questions?
There are also condensed matter examples.
Yes, yeah.
Maybe, for example,
I will come to one of them. Yeah, yeah, you're right about that. There are also condensed matter.
one more question about
Just a minute, take the mic, please.
one more question about your string. You said you can also consider thermal agitation.
Yes, yes.
There it becomes analogous to just summing all the possible conformations, for example, in a polymer.
Yeah.
And then you see that there's an attractive force.
That's
because,
correct. That's absolutely right. No?
Same.
So you can understand the polymer elasticity as a kind of effect that comes from the
So
fluctuations.
there what you do is just sum all the possible
Yeah,
conformations.
yeah,
right? And then
yeah.
you get a
So
finite.
DNA elasticity, for example, you can measure it by attaching two spheres and pulling the ends by optical tweezers, and you find there's an attractive force, which comes because when you stretch it out, the number of configurations are limited. And you can do the same thing with a rubber band. If you take a rubber band and pull it and put it against your forehead, you'll feel the heat, the entropy being thrown out of the rubber band.
I have one question. So, regarding actually physically understanding why you subtracted that E infinity.
Yeah, yeah. So in this case, it's clear with the two copper plates, right? When you move the plate from here to there, you're only looking at, so imagine bringing the plate from infinity. When the two plates are very far away, you don't expect any effect. Then you bring it from infinity, the total energy, the work that you have to do to bring it from infinity to here, if you differentiate that work, you'll get the force.
Right. Or I was thinking of if you have in the mechanical example that you started off with, if you have these two ends and they are attached by the string, you can think of them, those ends being attached to other strings which go to infinity.
Yes, you can do that.
And you would suppose that those strings actually don't produce any force, but
Yeah.
they actually do pull.
Yeah.
They actually do pull the ends apart.
Right.
But these strings, I mean, they pull them inside a little more than those pull them apart.
Yeah, that's also one way of thinking about it. Absolutely right. No? Yeah. So the strings outside are like the vacuum outside between the
You would
plates.
have expected them to not affect the ends, but they do.
Yeah. Any more questions? Especially from the back. Yeah, let's give the students a chance. No? Yeah. Okay. Okay, please go on.
Actually, I don't know whether you know what, as I am understanding this harmonic number minus 1 by 2 imagine using the estimate force.
Can you lower the volume? Yes, please.
As I am understanding, this is nothing but the normal ordering of quantum field.
Yes, that's true.
This is the normal order.
Yeah, yeah. So in quantum field theory, we do have to.
From
Yeah.
infinity, we are
Yeah.
expecting the finite part.
You're right, but it's beyond the scope of this talk. I'm trying to keep it at the level of, across the institute kind of level. Okay, now I can go on. I think I'll try to wind up. The conclusion is that, well, we started with the mathematics of divergence series, and we ended with the physics of the Casimir effect, and I showed you that these two effects were closely related. I started with a simple mechanics example because everyone has good intuition for mechanics that you developed when you were playing on the swing in the playground, but you don't have as much intuition for microwave cavities, which only came much later. But within theoretical physics, we regard everything as mechanics, whether it's electromagnetic fields or springs and atoms and things like that. The same ideas work for the electromagnetic field. The whole idea is, behind the Casimir effect is that quantum fluctuations have energy. I also pointed out that thermal fluctuations also do have energy, and as a result, as Pramod was pointing out, there are Casimir-like effects in polymer physics and many other kinds of soft matter physics, which is also one of the interests of this institute. Now, the derivative of this energy that comes from the fluctuations gives the Casimir force. To extract a finite answer for the Casimir force, we invoked two main ideas. The first was the atomistic nature of matter, the string, the waveguide, the plates. If you remember, I started out by lying to you that you had an infinite sum over all possible modes of the string. But then later on, I told you that that's false. The string does not sustain all possible modes. There are only a finite number of modes. When the wavelength gets smaller than the atomic spacing, there are no more vibrations of the whole string. There are only individual atom motions, and the total number of atoms is finite, and therefore there is no infinity in this problem. Similarly, when we talked about the waveguide, when you start looking at electromagnetic waves between here, at some point the wavelength becomes so small that you're in X-rays, and X-rays will pass through the copper plates. So there is actually a finite problem that we're talking about. We made it into an infinite problem by idealization. And the other thing I said, which is also not true, well, but this part is true, the matter is atomistic. The second thing I said, that only differences of energy are measured. Now, it's true that in the experiment that Casimir was proposing, there are only differences of energy. There's no absolute energy being measured. So absolute energy is not measured in most experiments. When you climb up the stairs, you're only measuring difference of your potential energy between being downstairs and upstairs. That's as much work as you have to do. Absolute energy would include your rest mass as well. And that's not being measured in such experiments. It's true of this experiment, but it's not true of all experiments.
Yeah, just a general question. So in all the physics examples that you've given, there is a fundamental cutoff that you have, right? Atomistic or to do with the structure of the matter that is there. And that's how you make this seemingly infinite object finite.
Yes.
Using a cutoff.
Yeah.
I can't see the link between that and what is being done in the mathematics case. In this use of the exponential function. Is
The
it somehow
exponential function was
there?
a cutoff.
Is like a
cutoff.
Okay, so is that the analog that we should walk off with? Okay,
that's right.
fine. All right, thanks.
So it was true of this experiment that absolute energy is not measured, but it's not true for all experiments. There are experiments in which the absolute value of the energy is being measured, and this cartoon, which was drawn by my daughter when she was about 9 years old, illustrates this point. Energy has mass, and mass gravitates. In that sense, energy also gravitates. So the gravitational effects of energy are actually a measurement of the absolute energy. It's not a measurement of the differences of energy. So within gravitational physics, it's not true that you only measure differences of energy. You are actually measuring the absolute energy, including the rest mass. So now we are moving to a slightly higher regime, which involves Einstein and the general theory, but I won't take it too high there. We computed the finite difference between an infinite sum and an infinite integral. The infinite integral was swept under the rug. What you measured in the lab was the difference between an infinite sum and an infinite integral. The infinite integral is actually the infinity which was really present, and I swept it under the rug, saying that you only measure differences of energies. And now let's get a closer look at the integral, which is, let's look at the elephant under the rug. We'll start with a simple example, the thermal fluctuations of a membrane, and this again goes back to what Pramod was talking about. Just like a string, a membrane can also vibrate. A drum vibrates, and a drum has got modes. There are lipid membranes, which I can get by putting amphiphilic molecules into water. They will form layers, which are membranes. And in fact, an example of such a membrane is a cell wall. A drum has different modes of vibration, just like a string. And if you go to the museum, you can see these modes very explicitly. Raman did experiments with tablas showing how the modes look when you have a vibrating drum, using sand to bring out the places where the modes have nodes. So if you can apply the same logic to a drum, you'll find that the infinite part, I'm not interested in the finite part now, which we've all done with. The infinite part is given by an integral, sum over all the modes, and this is the sum over all the modes, integral over the dx and dk, the wave number of the strings, divided by 2 pi squared. And every mode, every oscillator has got a thermal energy of kBt, Boltzmann's constant. And if you do this integral, the integral over x will tell you the area of the drum or the membrane, and the integral over the momentum will technically would have been infinite if you could take into account all the possible modes. But we know there's a cutoff here, and that cutoff, I'm calling it lambda inverse here. And this is now a momentum space cutoff, lambda. I mean, lambda is now a length. Lambda inverse is in the momentum space. And you find that the energy is proportional to the area. And so there's an energy cost for creating more area in a membrane. When you make a membrane bigger, there's an energy cost. How much is the energy cost? Well, that energy cost is what we normally call the surface tension. And if you calculate, you find that is equal to kBt upon lambda squared, where lambda is the cutoff. Now, surface tension is the same effect which you can see very clearly in a dewdrop. The dewdrop is round because surface tension wants the surface to be as small as possible. But of course, there's gravity, and the competition between these two effects makes the dewdrop slightly flatter. The surface tension is given as the energy per unit area and is given by this formula. Now let's put in this formula using the idea that the cutoff is actually given by interatomic spacing of the membranes. When you do that, you find that the Boltzmann, well, the kBt at room temperature is about 1/40th of an electron volt, useful number to remember. Lambda is about 10 to the minus 10 meters. And when you put that together, you find that the surface tension of a membrane you would expect to be about 40 millijoules per meter squared. And remarkably, this is the right order of magnitude for the oil-water interface. In fact, all interfaces have roughly this order of magnitude. But there are some interfaces which have a much smaller surface tension. Those they're called fluid membranes, and that's an interesting connection which I'll make later. But there's also, if you take much larger molecules, you find the surface tension actually decreases because of this effect. Now, returning to quantum fluctuations and the Casimir energy, the integral we subtracted can have gravitational effects. It was formally infinite, but we know that because of the atomistic nature of matter, it is really finite, as all physically measurable quantities should be. A similar calculation to what we did above, the sum over modes, gives us a value for the cosmological constant. So vacuum energy is made, I mean, you find that if you go to space-time and look at the action cost for creating space-time, it's given by the same kind of argument that we had just now, but this is the number, where this is a distance cutoff. At very high energies, we don't believe that space-time is continuous. There must be something replacing continuous space-time. The atomistic nature of space-time at a fundamental level creates a cosmological constant, or predicts a cosmological constant, which is roughly of this value. I'm not going into many details because I realize that people from the other groups, not the GR group, are not familiar with general relativity, and some of these arguments need GR to bring them out properly. The atomistic nature of space-time at a fundamental level is given by the Planck length, which is 10 to the minus 35 meters. The theory predicts a cosmological constant, a repulsive force that accelerates the expansion of the universe. We all know we have learned at school that the universe is expanding, but we did not know till the 1990s that that the universe is actually accelerating. It's not like a car which is coasting at a constant speed or slowing down. It's actually accelerating, and that would be a consequence of a cosmological constant. It was seen in the 1990s by looking at redshifts of very distant supernovae, but the value that is seen experimentally is 10 to the power of minus 120 times this number, which is predicted by the theory. So this is definitely a bad prediction, and we'd like to understand why. why this is so. Why is there such a difference between the theoretical expectation and the experimentally seen value? So this is actually a wide open problem for the 21st century. Understanding the cosmological constant from a fundamental point of view. Now there are some ideas about this, and this is my introduction. Idea proposed by Sorkin is that the cosmological constant is a finite size quantum fluctuation due to the discrete structure of space-time. Roughly speaking, if you take the four volume of the universe, you take the look back time up from now up till the Big Bang, and take that in explicit in terms of Planck units, you find that the volume of space-time is 10 to the power of 240. And this 1 over 120 here is actually a root n fluctuation. 1 by root n is the size of fluctuations which you get when you're talking about large numbers and fluctuations. That was Sorkin's prediction made in 1990, before the cosmological constant was actually seen experimentally. It was done within a particular approach to quantum gravity, which Sumati works on also, the COSET program. And it's one of the nice things which has come out of this program, that you actually predict an effect quantitatively. Of course, yeah, let me not dwell on that any further. And there is some work by myself and Professor Sinha, who's in the audience. We use an analogy between the cosmological constant and the surface tension of fluid membranes to understand how you can take this problem, which is set in the context of cosmology, and transfer it into laboratory physics. And this paper has a simulation of a fluid membrane, which actually measures the fluctuations in fluid membrane surface tension and shows that it goes as 1 upon square root of n. So I think I'll stop here since I seem to have run out of time. It's exactly 4 o'clock now. So we can take more questions after this.
So this diverging series, so any of these diverging series,
It's not all, I think.
and then put a cutoff, and then take some limit where you get a infinity and you get a finite answer.
Yeah, I think you hold it
So
perpendicular.
does it matter like what kind of cutoff you put?
No, it does not. You can show by integration by parts, as long as the cutoff is 1, that function that you use, f of lambda, it is 1 at low frequencies and 0 at high frequencies. Any form of the cutoff will do. Yeah. So Euler's arguments usually use integration by parts. And that means that you only worry about the boundaries.
So you need a function basically which is integer one. N goes to 0 at infinity and goes to some
One-
finite value.
1 at zeros, because you don't want to mess around with the series at low frequencies, but you want to get into the high frequencies.
Yeah.
And in fact, if you look at the terms that contribute to the Casimir effect, it's only the first 4 or 5 terms. The first harmonic, second harmonic, up to 5 terms. After that is negligible.
I mean, negligible when you say it is
I mean-
1 by 12 plus minus something? Or, no.
Most of the minus 1/12 comes from the first 4 or 5 terms. After that, it's beyond, like, when you measure to 1% accuracy, you can forget about the 6th harmonic and so on. Yeah. T.
And then Samson, and then I think it's not working.
Take this slide.
Okay, so just a quick thing. I mean, I remember there's something called dimensional regularization, where you just go off integer dimensions.
Yeah.
How do you kind of, do you have an idea of how to relate it to the kind of physical examples? Like, for example, the cutoff that you did,
Yes.
interatomic spacing or, the spacing of, but it's been something on my mind. So how do you, is there an easy way to understand why dimensional regulation works?
Yeah, for example, if that Ramanujam sum for 3 dimensions, we got n to the power of 3, sum over n of n to the power of 3. If you're doing it in d dimensions, you would get n to the power of d. And you use the Riemann zeta function at the value d instead. This is related to dimensional regularization.
What we do is into 3 plus epsilon. And
Yeah.
that sort of is the way we throw away the.
Yes, the infinity. Yeah. No, you're absolutely right. That's, it is.
I was just wondering if you had a
Not immediately, but it's definitely related, yes, yes.
Hi. Sorry. Okay. Actually, this regarding this force between two uncharged objects, like one is this Casimir force, and very similar effect is also van der Waals forces, like where no charge is required. So which is related to the dipolar interaction between
and the fluctuations of the dipoles.
Fluctuations of the dipole.
Yes.
But so these two effect
they're identical.
Okay.
So you can do this calculation in two ways, and the Russian school has worked a lot on this. Landau school, after there was a number of people in that school. If you take two plates, forget about copper plates, you take two polyester plates if you like.
Yes. Okay.
And even then the modes are affected by this dielectric constant here. You can do the calculation as I have done it here, or you can say each of these dipoles is interacting with that by fluctuations. You have fluctuating dipoles, and when they start fluctuating in correlation, they have an attractive force between them.
I see.
That explains the Casimir effect as well as this. There are two alternative ways. Either you can look at the sources, or you can look at the mediating fields, and the answers that you get are identical.
Okay, but one thing is this in Casimir effect, like both the example you gave, that bow and this one, that boundary condition is like their displacement is 0.
Yes.
But if you use this plastic or plate,
Polyester, yes.
there the field is not 0, right?
That's true. So it's not 0, but there's still a different boundary. When the wave reaches there, it has to oscillate at a different. Here you get a sine wave or something like that, and there you could get some other kind of wave there.
Some other, okay.
So it affects the modes. That's the main.
Right. Okay. Thanks.
I have two questions. Actually, one related to Shantana. So there is similar this Casimir polder kind of effect.
Right.
So
the Casimir polder force takes into account retardation between this. Yes.
Okay. No, that was another is that what you talked about thermal fluctuations and quantum fluctuation. Most of the experiment they will be present together. Means it's
If you do the experiment at room temperature, you'll see both together.
Even with cold atom, means there is some contribution to and more often than not, they are competing. For example, if you go to like modern day experiments, so means is there a conceptual way of distinguishing the effect, what part of it from the thermal fluctuations and
I think if you do it at two temperatures, you can certainly distinguish.
I understand. Yes.
So it's a combined effect of quantum and thermal fluctuation. That is true.
Always. Yeah.
So I don't. I can't easily think of a way to. There's no signature, if you like.
Yes. Means there is no distinguishing feature, is what I think. But is there something theoretically which says that? Well,
one thing is that if you could change the separation between the plates, because the quantum effect depends on the frequency, but the thermal effect is kT, regardless of frequency. All oscillate by equipartition. The thermal effect is just kT. And so if you could change the separation between the plates, you could distinguish between the quantum effect and the thermal effect.
How low temperatures one has to go so that both affect the order of magnitude?
I don't really know off the top of my head, no? It's at room temperature is mostly thermal.
Yes, mostly thermal.
Yes.
I mean, even if you're not room temperature, I don't know, like even in, I don't know, helium temperature.
Most of these experiments are at very low temperatures.
Yeah, but how low is the low? I mean, like.
No, wait. Even at room temperature, if you bring the plates close enough, you'll be able to detect the Casimir effect, because that depends on the length. The omega will go high. If the omega is high enough, those modes will not be excited by thermal effects.
Okay.
Right?
Competition between KBT and H bar omega. I mean, if KBT is much less than H bar omega, you are in the quantum domain.
That's right. Yeah. So if you bring the plates close enough, you can make omega beat the KBT. Yeah? And they do that. They bring it to very close distances, something of the order of angstroms. Or I mean. Yeah, that is true. That is true.
So that omega has to be large, but you cannot make omega
No. There are multiple modes inside. Will be there.
Are there any questions from the students? Yeah, there's one there.
Hi, I have one question. I did not understood the part where, okay, some of, say, some, some can go to an integration in the limiting case, right?
Yes.
So what's in the, you're subtracting the integration out of it, but still getting a finite part.
Yeah, that was the point. If I took the difference between the sum and the integral, let me just draw on the board. So let me suppose I'm drawing the function 1 upon x. And I'm also summing the series 1 upon n, just for, as an example, n equals 1 to infinity. So this integral, let's say, which is like log x or something, so the area we're talking about is this area, the difference between the integral and the sum. Is that clear? So in one case I look at the area under the curve, the other case I look at the area under this rectangular set, and there's some area left over there, and that is the minus 112 that we are talking about.
Okay, yeah, thanks.
Sorry?
That's a nice picture to think of, yeah. I think the location matters.
My location or?
Yes, your location. Yeah. So are there any other questions? Students? Others? If not, let's thank Sam for a really
Oh, thank you all for coming. Yeah. Thank you, Tarun.
Thank you, Sam, for
One thing you can see is that it has mass and gravitates. Definitely.
And there's a high T